Hello guys, how are you doing today? So today I'm planning on talking a little bit about different methods that exist for analysis of indeterminate frames, and particularly for rectangular frames. I'm gonna be talking about three different methods, but this first example, it deals with the Portal method. And the Portal method and the Cantilever method, which is the next video that I'm gonna produce, are used for rectangular frames, indeterminate frames under lateral load. Then we're gonna study some assumptions also for vertical load, and after that we're gonna talk about how you can combine the methods in order to do a rectangular frame with vertical and horizontal load. Let's see what happened. So today we're gonna start talking about the method of the Portal method. And the Portal method was developed in 1915 by Albert. Maybe it was developed before, I don't know, but it was presented for the first time in 1915 for Albert Smith, and he presented that in a journal. He presented his work in a journal. It was a journal of the Western Society of Civil Engineers. That was the method that he presented, the method, the journal that he presented the method. Now, what he did is basically establish some assumptions for this method. What are the assumptions that he established for this method, which are good assumptions? And I know this is the time of computers and Pokemon Go and everything else, but I want you to get a taste of how was this and that time, and show you how accurate, within of course all the limitations, the method can be, and give you a good sense of what type of assumptions you can do in different cases. So if you have a case like this, something like that, we have learned from statics that this is a statically indeterminate frame. Statically indeterminate frame, you have four reactions. You have one reaction here. Well, this force is going to produce a moment like that, so I'm going to put the correct direction of the reactions. It doesn't matter if you don't put it, but let's say these are the correct, this is A, this is B, this is the correct direction of the reactions, countering the moment over there, and then you're going to have two also forces in this direction. So AX, AY, BX, and BY, and then you have that, and then you have 1, 2, 3, 4. So you have 4 reactions, 3 equations. There's no way that you can solve this at least for statically determinate. Of course, you can use different methods, like you can use virtual work method or energy methods, or you can use computers, and you can use matrix analysis, slope deflection, moment distribution, etc., 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 and solve that, which will be fairly easy because it's a small example. Now, what happened here is, if you deform this, if you apply this force in this way, and you study the deflection or the deformed shape of this frame, the deformed shape of this frame is going to follow something like that, and then here is going to come in, I don't know, something like this, and here is going to go again in that direction. This is going to be 90 degrees, 90 degrees, and it's going to be something like that. But if you look at this shape, you can see there is an inflection point somewhere over there, somewhere in that part. That's an inflection point. And what happened, and you know that because you have done tons, hopefully, you have done tons of shear moment diagrams, that whenever you have an inflection point here in that part, that could represent that you have an internal hinge in that structure. So in that inflection point, basically what you have is the moment is going to be 0 in the moment diagram at that point, and that happens when you have a hinge. So then if that happens when you have a hinge, why not to consider that point as a hinge, and then that frame that we had, that frame is gonna be changed somehow by this frame. Now, if this is our situation, and this is what we have now, Well, you have 1, 2, 3, 4, same reactions as before. But now this is a hinge at that point. And we introduce that assumption over there. If that is a hinge over there, in that point, then we have 4 reactions plus 3 equations plus 1 hinge, 4 equals 4. Or you can say, oh, how many reactions we have? 1, 2, 3, 4, 5, 6 reactions. R equals 6. Bodies is 1 and 2. N equals 2. So 6 equals 3 times 2. That means that we made an statically indeterminate system. We converted in the determinate system just by introducing that assumption. Now that hinge is going to be approximately located, if these are lateral loads, this is going to be approximately located at half of the length. And you're going to say, why am I going to go through that much trouble in order to do that? Well, if you do that, by the way, if you do that, then your moment diagram for this structure at the end is going to be something like this. And with that moment diagram and with the shear diagram, then you can start solving your problem and doing the design of the problem. That's only because I have one redundant here. Now let's check another case really quick. And the other case, then I'm going to have something like that and something like that. And I'm going to put the same lateral load here at this point. So if we have the same lateral point load at that point, then the deflected shape of this structure is going to be something like that, and then something like that, and here it's gonna go like that also, kind of something like that. And how many reactions do you have? Well, in this point you have here AX, you have AY, you have BX, you have BY in this direction, BY, and this point you can say is C, and this point you can say is D. And now, because this is a fixed support, you're gonna have also a moment. I'm gonna imagine the moment A here and the moment B like that, moment B like that. So you're gonna have these 1, 2, 3, 1, 2, 3, 6, 3 equations. It's statically indeterminate. Of third degree of indetermination. If you want to apply the same thing that we did before, then you have 1, 2, 3, 4, 5, 6. 6 R equals 6. One body only, and 1 equals N. 6 is bigger than 3 times 1 of an amount of 6 minus 3 equals 3. That means that is indeterminate of third degree. That's what we did before. Now, if you look closely again to the deformed shape, then it happens that you're going to have inflection points here, here, and there. And if you do the same assumption, then you can say that those inflection points are going to behave like if I have a hinge introduced in my frame. First of all, it's not going to be unstable, and secondly, it's going to be statically determinate. Is that statically determinate? Let's see if it's statically determinate. If I consider those hinges, and once again, the hinges are going to be at the center of the elements, approximately. It's not exactly at the center, but I can live with certain amount of errors because of all the factors of safety that we have in engineering. So if I put that at the half of each one of the lengths, whenever I have the condition fix inflection point over there, then I'm going to have how many reactions? Reactions equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 12. 12. How many bodies I have now? Well, now you have 1, 2, 3, 4. 1, 2, 3, 4. N equals 4. R has to be equal to 3 times N. R is 12 equals 3 times 4. 12 is statically determinate. So that means that we can do that. Most of the problem, or a lot of problems, and of course the moment diagram here should be something later like, I don't know, like this, and like then like that, the hinge, and then here also something like that. Most of the problem that you have here, or people have here, is knowing the deflected shape. How the deflected shape is like that? Well, you know, it takes time to understand that. It takes time for you to see how the deflected shape is. There are some, in every book, there are some conditions that you have, and you say, oh, well, if this part here is a fixed support, for example, and this is subject to lateral loading that way, the rotation here is 0, the translation here is 0, so that means that my deflection has to start from this point, almost 0, or almost 0, no, it has to be 0, rotation 0 here, and then because this is going to produce a moment in this direction, then this is going to deflect in the direction of the moment, something like that. But that's another topic, but you can see that. I don't know if I have, my desk, I have a bunch of things. Let me see, this is one of my cards, for example. If you put this card here, and let's say that you apply that load, but I'm gonna fix that load over there in that position, and I apply this load here. When I apply the load, this is gonna be the deflected shape in that part, you see. Now if this is a pin support, it's not the same, because if this is a pin support, now this is a hinge, and if I have something like that, of course I have to have some restrictions here in the other part. Let's say another hinge, for example. If I have another hinge, or I have some type of restriction from here, because this is a frame, let's say that this is offering some restraining in that direction, but this is a hinge. If this is a hinge and I use the same card that I used before, now it's only going to be a pin here, and when I apply that load, it's going to come like that. I'm going to have rotation at this point. I should have something here, let me see, in my trash can. It's not my trash can, actually, it's my pen holder, pencil holder. Look at this is perfect, and I should have some thumbtacks also. Look at that. You know what is this? This is from the eraser, but this is what I was telling you. If this is just, I'm gonna put the hinge there, because this is what a hinge is. So if I put a hinge there in that point and apply the load, this is gonna be the diagram, you see. Assuming that you have some restraint here, the diagram is gonna show this shape, which is the shape that you can find basically in every literature explaining you how the shape is like that. Now if I move it to this other side, and I put the same hinge there, but I think I pierced my desk. Okay, I put the hinge there, and I fix this in both sides. I don't know how I'm gonna fix it, with two, I don't know, popsicle sticks that I have from a competition that we did recently. Let's say that I fix these other parts here, and I apply the same thing. Now you can see the shape over there, you see? The shape start from here fixed like that, no rotation, no deflection, no anything, and behaves like that. So if you know that, and if you can understand what is that, the method of the portal is really easy, because you can put the hinges wherever the inflection points are. And if you don't know that, it doesn't matter, because every time that you see a condition that you have fixed, and this other condition here is also considered fixed or semi-fixed. Why do you mean fixed or semi-fixed? Meaning it's not a hinge. If it's a hinge, forget it. You don't do this type of behavior, because it's hinge. So if this is a hinge and this is a hinge, this will be displacing basically without no deformation there. But in this case, if you have this part here and you have the load and this is restraining it, and you apply this load, this type of shape is going to happen. If you have this type of condition, always you're going to have to put a hinge at the middle. If you have hinge, you don't need to put any hinge, because if I put another hinge here, that will be unstable. But if I have this hinge here, or this pin here, and another pin here, which is the previous example that we did, at these points I don't have any indeterminacy for saying it in that way. But this behaves like fixed, this part behaves like fixed. So these two parts, when are gonna do that, and I'm gonna have the inflection point there. So this is what you have to check. That's it. So the method of the portal is very straightforward, and so far I only show you with two. But what if you don't have two? What if you have now three? And this is fixed, and this is fixed, and this is fixed. Well, if you have three, now you have 3, 6, 9, 9, three equations is indeterminate of 6 degrees. That, if you have to solve that by hand and apply redundance and apply superposition, that's a nightmare. You're gonna be working there for 3 years maybe in order to solve that. You know me, I'm exaggerating, not 3 years, but if you apply the method of the portal, well, the first thing that you will introduce is hinges, 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 and hinges, and you have the lateral load here. So if that is the situation, now you have 1, 2, 3 times 3, 9, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, yes. So you have this, and that will become statically determined in that way if you do it like that. Be careful with this, because depending what you put, you can make it unstable or non-stable, but this is basically what you do. Now what happened now, and how do I solve this? Well, there is another assumption that you do here. The other assumption that you do in order to solve the method of the portal, because forget about this now. Now think of that, something like that. Imagine that you have something like that now. If you have something like that and you have to start by solving this, well, hinges everywhere. That's what you have to do. You put hinges everywhere. You put hinges, 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 hinges. Every single half length, you have to put a hinge. And now how do you solve that? Well, there is a second assumption. The first assumption is you have to place hinges at inflection points. And the second assumption then is that if this is on the lateral load, and that kind of makes sense, if this is on the lateral load and you study shear now, the exterior columns are going to receive less shear than the interior columns. And the method assumes that the interior column, because they are taking the shear, or the axial will become shear from these two beams in the two different directions, then the shear here is going to be double of the shear here. And if you check the buildings, usually under this type of loading, these columns are bigger also than the other columns. And the reason for that, or one of the reasons for that, is the shear, and the reinforcement for shear is also bigger. So you assume that the shear here is double than the shear here. If that is correct, and you have hinges placed, for example, at this location over there, I can make a cut in that part. And if I make a cut in that part and I separate the top part wherever the hinges are beautiful, because you know hinges, there's no moment in that hinges. So if I have this force here, P, and I somehow assume that the shear here is half of the shear here, or the shear here is double of the shear here, I can say, oh, this is my one shear, this is two shear now, this is two shear, and this is one shear. And guess what? Just by doing summation of forces in X in this portion, of course I'm gonna have here these the other forces and the no moment because it's hinges, but I'm looking just at the horizontal part. So if I do summation of forces in that direction, then I have 1, 2, 4, 6. P is gonna be equal to 6 shear. Of course I know how much is P, so P divided by 6 in this case is gonna be my shear, and I already know that value. I calculated that value just with that simple equation, doing that simple assumption. I don't know if you're getting the point where I'm going at, but with these simplifications, solving a monster like this is not going to be difficult. You have to work for it, but it's not going to be difficult. So let me show you how a real problem will be done. And by real problem, I mean I'm going to do not the monster as big as the one that I put over there, but I'm gonna solve a smaller monster, let's say. I'm gonna try to show you a problem like this. And then you have an intermediate here, and then I'm gonna put two columns, which they are gonna be also fixed, and fixed support here. Force of 20 kilonewton and 40 kilonewton here. Distances are 1, 2, 3, 8, 6, 8 meters, and distances here are 4 and 6 meters. And then we have to solve these type of problems by the method of the portal. I have a bunch of indeterminacy there, bunch of indeterminacy, because this is a closed loop, so you have to close the loop also. You have 3, 5, 6, 9, 12 times 2, 24, 24, and then you have 1, 2 bodies, you name it. So big, so many redundants. So how do we do that? The first thing that we do is place hinges. Where are we going to place the hinges? At the midpoints of every single element. So first, place hinges at inflection points. Remember, this is fixed and this is considered also fixed, semi-fixed. So if I have a hinge here, that would be different. But I don't have that hinge, so that's one of the things also the method of the portal, that has to be all the connections like that. So then I'm gonna put I know the inflection point, as I showed before, is gonna be at the center of every element. Every element. This is the way the structure is gonna basically look like. And the first step is that, which we already did. The second step now is calculating the shear, because it's the easier. The shear force is the easier one. How? I'm going to pass a section through the first level, or the top level if you want to say it like that. And if I do that, in my drawing, I'm just gonna not place those hinges everywhere, just for not over complicating, and because they don't affect the calculation that I'm gonna do now. But you know what you have, this is basically this, and here in these hinges that I artificially introduced, I know I'm gonna have moment, I know I'm going to have one vertical force also, but this calculation is dedicated only to calculate the shear. So I'm just gonna consider here my shear in this direction, and we say that the interior columns takes twice as much shear as the interior columns, as the exterior columns. So this is 2, 2, 1, 1. By shear, remember, I'm gonna put it here, interior columns take twice as much shear as axe. I'm kind of thinking of an axe now, as exterior columns. That's what I did here. And if you do that, then you have that summation of forces in X equals 0. So you can say that 20 minus 1, 2, 4, 6, 6V1 equals 0. Or V1, the shear at that level now is going to be 20 divided by 6, and 20 divided by 6 is 3.3. There you go. Look how easy it is, this kilonewton. That's going to be the shear here. So that means that here I'm going to have 3.3, but here I'm going to have 6.6, 6.6, and 3.3. That's basically what we have there. Now, that's at that level. The second or the third step will be, okay, if I did that, now I'm gonna keep the first two stories and I'm gonna make another section here in the second story. I'm going to apply the same assumption. So if I do that for the second, I can use this one. I use just this section. I don't care, but it's easier if you just consider it now like this. and you make the cut at those hinges in this part. So this is going to be 20 and this is going to be 40 because those are these two forces here, 20 and 40. And same assumptions, interior columns take twice as much as exterior column, so this is going to be the shear at that level. This is going to be 2 times the shear at that level. This is going to be 2 times the shear, and this is going to be the shear. And we do the same thing. So now we say summation of forces in X equals 0. If we do summation of forces in X equals 0, we have 60 in this direction, and in the other direction you have 1, 2, 4, 6 equals 6 V2, meaning V2 is going to be equal to 10 kilonewton, and then that means that this value is going to be 10, this value is going to be 20, 20, and 10. So look how many internal forces we already calculated just with two easy and simple summation of forces in X equals 0. Now a little bit of imagination comes into play, and now you have to start solving that monster frame. How do you solve that monster frame? Well, it's up to you. I can't show you, I can't teach you how to do it, but somehow I can show you how I do. And this is what I'm going to do now. I'm going to create the same frame, but I'm going to cut it in all the joints and all the members. So I'm going to try to do the same drawing that I have here in joints and members and everything. So this joint is the joint that I haven't put any name into the joints. Let's put names to this, and let's say this is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Okay, there you go. So this will be the joint I, and this will be the member E, I, E, and this will be the joint E, and then this will be the member EA here, and then that's it, because you have here the reactions at the bottom. So this is this part here, and then you keep doing the same thing here, and then you put your element there. It's gonna be like that, and I think my paper is gonna be too short for this, but I don't know. Then I have the joint here, I have the other column here, this other column here, and I have another column here, and I have another column here. I don't know why I selected this example. This is too big for this. So I'm going to have these here also, and here, here, and here, and here. Of course, you have the same joint in this other part, but the analysis of the joint in this part is not important because I don't have any concentrated force. I need these definitely because I have that force of 20 there, and I need these definitely because I have that force of 40 there. That's why I'm isolating the joints in this part and not in the other parts. So then you have that, and then you have these, and then you have the columns here also. Oh, I forgot my hinge. Where is my hinge? Don't forget my hinges. Okay, here, here. What a nightmare. Okay, look at that frame over there. Now we start with what we know. And what we know from before is that at this level, my shear is 10, 20, 20, and 10 at this level. So if I have to get this little piece here, for example, this little piece here, and I know this, and we calculated that this is 10. Well, if now I study the bottom column, if the bottom column is like that, this 10 is going to be transferred to this side as 10, and in this part, I'm doing just this portion of the hinge. Okay, if this is 10, at the bottom here, I'm going to have a shear of 10 also. Here, this 10 is going to be the same 10. And because this behavior is going to repeat in the other columns, So previously I calculated this 10, 20, 20, 10. So I know that this is going to be 10. This is going to be 20, 20, and 10. And guess what? Same thing is going to apply at this intermediate level. So this intermediate level, if that work here, and I calculated that, that means also that this value here, I know it, 3.3, repetitive, periodic, 6.6, 6.6, and 3.3. That's what we have there. And those are the calculations that we have so far. Now, what do you do after having this mesh? Well, after having this mesh, remember this is a fixed support. If this is a fixed support, I have to have axial force here, axial force here. I have to have moment. I have to have axial. I have to have moment, axial, moment, axial, moment here also. Same situation with everything else. But now somehow we can start completing this. Why? Because I know that at this end also I'm going to have axial, this end axial, but I'm going to have also shear, and at this end I'm going to have also moment. Now if I look at this column that I did here before, and I know this is 10, the only other force in this part is this 10. That means that this has to be 10 by summation of forces in X. And this force is transferred now to this joint opposite, like that, as 10. Oh, but wait a second. If this is 10, I have a concentrated external force of 40 applied there, meaning that if I do in this joint summation of forces also, what happened is that I need something here and I need something here in that joint. I have an axial force coming here from this beam, and I have another axial force coming to this joint from this column. Now this 3.3 is going to be transferred to this end, 3.33 in the opposite direction as I had it before, 3.3, like that. The only unknown is the force here, horizontal force, that is going to be the axial in this beam. But I have all the others, so I have 40 in this direction, 3.3 in that direction, 10 in this direction. So 43.3 minus 10 is going to be 33.3, meaning the value for this reaction has to be here, 33.3 in that direction, which is going to be transferred to this other beam in the other direction, 33.3. This is like completing. This is a structural Sudoku. The only thing is that they don't have to add from 0 to 9 in every single part. So now I'm gonna go here. This is 3.3. I don't have any other force here, meaning this part here is gonna be also 3.3, like that. And this one is gonna be transferred to the joint as 3.3. Now here, this joint I only have 3 forces, this one and this one and this one. That's it. And this is 20 applied there, external force, and this is 3.3. I know that this force has to be in this direction for equilibrium in X, 16.6. And I know the same force that is 16.6 here is going to be transferred to this beam here as 16.6 in that direction. Which you can continue and say, oh, but if this is 16.6, then this is going to be 16.6 also in that direction. And now here you have to take a knee and wait a moment. Why? Because I can't say that this is 16.6 because I have 1, 2, 3. But in this case, if I look at this one, this is 6.6. I know this is 6.6. And if I study this joint here, which I didn't copy because you don't need to copy it, but if you want to copy it and study the joint independently, you're going to have that joint is going to be something like that. And if this is 16.6, this is going to be 16.6 in that direction. And if this is 6.6, this is going to be 6.6 in that direction, meaning that in the joint I have to have this force here of 10, and that force of here of 10 is going to be transferred to that beam in the other direction of 10, like that. 10. But you don't need to do this because you could have figured it out from here. Look, 6.6, 16.6, I need 10 in that direction. Now, what happened now at the end of this beam? Well, at the end of this beam, I'm gonna have the same 10 in the other direction, because I'm just doing summation of forces in that way. And here, if this is 6.6, this is gonna be 6.6. And if this is 6.6 and this is 10, how much is this? Come on, tell me. Nope. Yes. You're gonna say, who is he talking to? I don't know. 3.3. So 3.3 plus 6.6 is 10. 10 minus 10 is 0. And then you go to this one, and you know this force here is gonna be also 3.3, because the summation of forces in that direction. And if this is 3.3 in this direction, it has to be 3.3 in that direction. And if you can compare now, well, if it was 3.3 here, it has to be 3.3 there, but I already knew it was 3.3 here, so that means that yes, everything is going correct so far. Now, we have to complete these forces here. If this is 20, yeah, 20, that's easy. If this is 20, how much is this? 20. Now this is 10, 10. We haven't done the moments yet, but we are, look, all the forces, internal forces that we have already. Basically, we are almost done with our shear and axial, for the shear and axial moment diagram. So 33.3, how much is this force? Guess how much? 33.3, the other direction. I don't have these two here, but now look what happened in this joint. This is 6.6 to the right, I mean 20 to the right, 33.3 to the left, 6.6 to the left. How much is this? 6.6 periodic, 33.3 periodic, 40 to the left, 20 to the right. That means that I need, in order to do equilibrium here, 20 to the right. Don't get confused or you say, oh, this is 20 and this is 20. No, this is not what I'm doing. I'm doing summation of forces in this joint. Positive 20 minus 33.3 minus 6.6 plus this variable or this load equals 0. You solve for that, that is 20. Now you go to this other end. If this is 20 at this end, the other end has to be 20. Summation of forces in the element action reaction. So 20 here. And now you have 20 in this direction, 20 in that direction, cancel each other out. This is 6.6. The force in this other direction has to be, you guessed correctly, 6.6. And now I have that. Last but not least, and this is like a checking joint, if you want to call it like that. But let's see what happened here. I have 10 in this direction, and I have 3.3 in this direction. This is 6.6, right? In this end, this other force here has to be 6.6 in that way. Now check, 3.3 plus 6.6, 6 to the left, 10 to the right, 10 to the left, done. And we completed so fast every single force in that direction, but we haven't gone yet to the other forces. Now we're gonna go there. Now, how do we do that? Well, there are several ways that you can start this puppy, and it depends in what you want to do. For example, and I'm not telling you that I'm gonna keep going in that way, but for example, let's say that I wanted to find this moment. That moment is really easy, really easy to find. How come that moment is really easy to find? I have to find everything else. No, you don't have to find everything else. Because if I needed to find that moment, for example, I can just make a cut here and study this portion of the beam. I know this is 10 because I already calculated, right? I know this is my axial force in A here, and I know there is a moment at A right there. And I know there are going to be some internal forces which, guess what? I could care less about that, because I'm going to do summation of moments at that point. Do you know what is the height of this frame? Yes, we do know. We know that that frame is 6 meters in height, and I know that I put the hinge at half the column distance, the column height. So I know that this distance is 3, meaning I know that this distance is 3, meaning that if I call this point A prime, for example, and I do summation of moments at A prime equals 0, then I'm going to have, and I say this is positive, I don't know, negative 10 times 3, negative 10 times 3 plus MA equals 0 and MA equals 30. Remember, from time to time, put the units kilonewton meter, but imagine if this is a mess if I start putting units everywhere. So this is 30, that moment. Easy peasy. I know this is 10, right? I know this is 30. If I want to calculate that moment, how do you calculate that moment? Well, you do summation of moments here in the whole structure, and then you say 10 times 6, how much is that in this direction? 10 times 6 in this direction, 60, right? 60. And this is 30 in the other direction. Guess what? I need 30 in this direction. Do not, and I'm gonna make emphasis in that again, do not say that because this is 30, this is 30. This is not what I'm doing. I'm gonna do it here again, because I know there is a lot of confusion, and I know I'm going fast, but even if I'm not, imagine if I'm not going fast, how long it's gonna take to solve this if I have to go every single step. And not even that, imagine how long it's gonna take you to solve a problem like this in one midterm. So you have 10 here, and you have 30 here. And I know I have these axial forces, but I don't care too much now. I know this force is 10 over there, and I'm not putting my hinge over there, even though I could, because I could have done the same analysis that I did before. I could have used the top part, but I'm showing you with the bottom part. So I say this distance is 6, this is 30. Summation of moments here, I don't know what point is that. That point is E. Summation of moments at E equals 0. If I do that, I'm going to say that negative 10 times 6 plus 30 plus my moment equals 0. So ME is going to be equal to 30. Or I could have used the same hinge and say, you know something, I'm just gonna put the hinge here, put this here, put this 10 here, and I know I have a moment E there, and then I'm gonna do moment here. If I do moment here, I'm going to have the same equation that I got right there. So I'm gonna have 10 times 3 in this direction, 10 times 3 in this direction, negative plus ME equals 0, so ME equals 30. The same thing. You do not have to do this every single time. You can see it here and say, oh, wait a second, I do moment here, 10 times 3, it has to be 30 in that direction. And now you have these, I mean the moment, and you have the moment. My thinking for this problem, the easiest part to me is starting maybe, I don't know, if you want to start here, you have this force here, you have that force over there, that change there. You can go and calculate the moment here in the same way that we did the rest. So I can say moment here, how much is my moment there? Now remember, this distance here is going to be half, which is going to be 2. So this is going to be 2, and the bottom one is going to be 2 also. So let me use the red pen. If I have to do the same approach that I did here, and I have to apply it at this point here now, I have a moment somewhere here in this part, and I can say summation of moments here equals 0. So I'm going to have a moment in this direction, which is going to be equal to 3.3 times 2. So this moment is going to be 6.6. And if I do the bottom part here, then I'm going to have the same thing, because this is 2, and this is going to be 6.6 in that part. So this moment here should be also 6.6 in this way, because it's the same, right? I'm studying the moment here, but this moment is not going to be transferred like that. And I don't know if you are starting to see the pattern that is emerging here, but the moment at the end of every one of the columns, if you use this method, is no other, and I'm not saying the beams, the girders, I'm saying the columns. The moment at the end of the columns, and every time, is half of the height of the element multiplied by the shear that you found before, and that's gonna happen everywhere. And if I know that it's gonna happen everywhere, then I know the moment here is gonna be what? 6.6 times 2, 13.3. And here how much is gonna be? And it has to be opposite to this, of course. This is going in this direction, it has to be opposite in the other direction. 13.3. And here, same thing. 13.3. In this direction, 13.3, because this is like that. This moment has to be opposite. I don't know. I put it like that and you didn't tell me anything. Like that, opposite. And this one is like that and has to go in the other way. 13.3. And this one here, if this is like that, the moment has to come like that. And the moment here, this is 3.3 times 2. This is the action. The reaction has to be in the other direction. 6.6. And same thing here. This is the action. The reaction goes in the other direction. 6.6. And we finish basically with those. And here we have to do the same thing, because if we have 10 times 3, here I'm going to have 20 times 3. So that means this is going to be 60, this is going to be 60, this is going to be 30. At the other end, same situation. This is 60, so the moment is going to be 60, 60, and 60, and 30 because this is 10 times 3. And now I have this. What else am I missing here? Okay, there you go, cracking my neck. Okay, we finished everything, but I still don't have anything related to the axial forces, so let's see how we can deal with that. But look how complete and how messy this looks with all those values. I'm proud of my messiness. Okay, now, if you do this, you have this here, you have this here, you have this here, you have this here, but look at this moment. This moment is 6.6 in this part. That means that if I transfer this moment, I don't have any concentrated moment anywhere. So if I transfer this moment to this other end in this part, I'm going to have a moment. If this is like that, the moment is going to be here like that. 6.6 in that way, and in this part I'm going to have another moment which I don't know what it is, because now is when we start working with the other reactions that we have here. Now I know that here I'm going to have a reaction in this direction or in the other direction. I don't know what is the direction, but now if you check, and I'm gonna do that just for this time, if you check this hinge and you have this reaction, which I don't know what is the name, but I'm gonna say IY, and I have that force over there, which I really don't care too much, but that force is 16.6, and I have this moment in this direction, and this moment is 6.6 in that way, 6.6. I know that here I'm going to have another force like that, and I'm going to have another force like that, correct? This, I don't know if this is the point, how do I call that? IJ, I'm here in the point I prime, maybe. If I go to I prime and I say summation moments and I prime equals 0, I'm going to have, and I say this is positive, I'm going to have IY times this distance, oh that hinge, I place that hinge at half of the length. And what is the length? The length is 8, so that means that this distance from here to here is 4 minus 6.6 equals 0. My IY then is going to be 6.6 divided by 4. Calculator 6.6. I don't know what I'm doing that if I know that that's the value. Okay, 1.6. So that value over there is going to be 1.6. you're gonna say, oh my god, that professor is dividing 6.6 in the calculator. Actually, I was making time because I received a WhatsApp and I was checking it. Now you know my secret. Okay, so this value here is 1.6. Beautiful. I know that value over there. Now everything is gonna start showing because I know this value here. Now this is the one that I just calculated. This is 1.6, and if this value is 1.6, how much is this value? You got it, 1.6. Yay, 1.6. Now remember what happened here. I don't know what is gonna happen in this part. Also, how do I transfer this to that? I need to know this, and I don't know that yet. But now I can continue in this other end, because if this is 1.6, I know here I'm going to have what? 1.6. And how much is going to be the value here? 1.6. You guess again. 1.6. And now I have this joint here, and this joint is going to change everything like before. Like before it happened. So, because I have 1, 2, 3. But guess what? I can do the same thing that I did here. And I say, you know something? I know I have a force here. And you know something else? Oh, where's my moment here? Wait a moment. I didn't put my moments in this part. Why I didn't put my moments if I knew how much was the moment? You see? This is 6.6. This is 30. Same direction. Same direction. I need a moment of 36.6 in this direction. Like that. Now I have that 36.6. If I do at this point summation of moments at this point, and I'm gonna relate it to this portion of this frame, then I know that 36.6 divided by this length is gonna give me that. How much is this length? I just said it before, that length is 4, and if I divide 36.6 by 4, that's gonna be 9.16. And I don't know if you realize it again, but another pattern is emerging. Whatever moment I have here, I just divide it by half of the length, and it's gonna give me that reaction over there. Now if that is 9.16, you continue to this end, this is 9.16 also here, right there. Okay, now I can calculate the moment at this end. How do I calculate the moment at this end? Well, I can say summation of moments at this point equals 0 to this side. So I'm gonna have 9.16 times half of the length. How much is 9.16 times 4? Because this distance is 4. 9.16 times 4 in this direction, and then I'm gonna have the same opposite moment in the other direction, like that. 9.16 times 4 is 36.6. So that's my moment there. Now if I know this moment, and I know that moment, and I know that moment, I can know this moment. This is what? 60 in this direction, 36.6 in the other direction, 13.3 in that direction. This is 20, 33, 33.3, 36.6 in this other direction. So you have this is 60, not 20, 60. 20 is this reaction, 60, 60, 73.3. Let me do it here. No, not here, here. That is already a mess. So this is gonna be 60, and this is gonna be minus 36.6 plus 13.3. How much is this? This is 40, 73.3 minus 36.6. Oh, half. Okay. Negative 36.6. Okay. So that means that I need another 36.6 in this direction. Now once again, this is not 36.6 because this was 36.6. Okay? This is 36.6 because I did summation of moments there. Now if you go here, I need the value of this force. How do I get the value of this force? Well, I divide 36.6 by this distance. As I said before, the moment here, you divide it by the length. How much half the length? How much is the length? 6. Half the length? 3. Meaning this distance is 3. 36.6 divided by 3 is 12.2. This is the value of the reaction here, 12.2. Summation of forces in Y. How much is the force here? 12.2. How much is the moment in this end? Well, the moment in this end is going to be what? 12.2 times 3, 36.6. This is the action. The reaction has to be in the other direction. 36.6. I hope that you are a little bit more organized than I am. 36.6 here in this part. Here I can do the same thing. Now I can add the moments because I have this moment, this moment, and this moment. This is 60 in this direction. This is 36.6 in that direction. This is 13 in the other direction. So the same thing as before. This is going to be 36.6. And if I want to know how much is the vertical force here, it's going to be 36.6 divided by this distance. But now this distance is half of 8, which is 4. So if you divide 36.6 by 4, you know what I'm doing, right? I'm gonna do it again here for this part, just in case you are getting lost. So I have this 36.6, this is this, and this distance is 4. So if I need to know how much is the value of this force, I don't know, I'm gonna call it, I don't even remember what joint I'm working. This is joint G, so this is gonna be GY for saying something. If this is GY, I can say summation of moments at G prime equals 0. So this is going to be 36.6 divided by 4, because I'm going to have GY times 4 positive minus 36.6 equals 0. So GY is going to be 36.6 divided by 4, which is 9.16. 9.16, that's the value of the reaction, which is what I told you before. You don't even have to do this every single time. You just have to calculate your moment correctly, divide by this length, and then you're gonna have the value here of 9.16. That's what I said before, 9.16. 9.16. What is the value of this other end? 9.16. What is the value of the moment here? The value, I can write more in red. What is the value? This looks like one of my S's when they're correcting it. Everything is red. So this is 9.16 times 4. So the moment should be here. 9.16 times 4 in the other direction, which is 36.6 in this direction. Now I have this moment, and this moment, which it adds up, because this is 30 in this direction, 36.6 in that direction, 36.6 in this direction minus 36.6 in that direction, 0. Summation of forces in Y, where I am at now. Let me see. I have this, I have this, I have this force, I have this force, I have this force here. I need to continue with my moments. If I continue with my moments, then I can use this n, I can use this n, I can use this n, right? Basically, I just have to complete every single one of the forces that I have over there. How do you do that? I don't know. I mean, you can start from, you know, this one here in this n. Is there any way that I can know how much is that? Well, if I know the moment, is there any way that I can know the moment here? Of course you can know the moment here. How much is the moment here? 1.6 multiplied by this distance. How much is 1.6 multiplied by that distance? That distance is 4. 1.6 times 4. This is the action. The reaction goes here. So this is gonna be 6.6 again. 6.6 in that way. And if I know the moment in this way and know the moment in this way, this moment is 13.3, this moment is 6.6, and that means, by the way, this moment, yeah, this moment is the direction of the moment. Yeah, because this is the action, this is the reaction, 13.3, and I did it like that, I don't know why. So 13.3 in this direction, 6.6 in that direction, meaning I have to have 6.6 in this direction. And if I know this is 6.6 in this direction, and I know this distance, which is 3, then I can know the value here, which is 6.6 divided by 3, which is 2.2. And if I know this 1.6 and I know this 2.2, I know how much is going to be transferred to this other joint here, which is going to be 2.2 in this direction, 1.6 in that direction. I need 0.6. I am messed up with those periodics. I think it's 0.5 something, 56. 2.2222222 minus 1.666666 equals 0.5 periodic. So this value should be 0.5 periodic here. And if this value is 0.5 periodic here, this value is 0.5 periodic here. And then I can continue with the same thing. I know this, I know this, I know that. Summation of forces in that joint. So this is 3.6 in that direction. And guess what? This value is 3.6 in that direction. Do the same thing here. I have this value, I don't have the vertical one. Yes, I do have it because I calculate that 1.6, meaning this one here has to be the same 1.6. If this is 1.6 here and this is 9.16, when I transfer it to this way, this is going to be 10.83, and it has to be in this way, 10.83, and summation of force in this direction, 10.83. And I'm tired. Okay, you continue it and you finish it. I don't want to do and don't want to waste time anymore here because I explain every single one. I'm gonna give you how much is this value. This value is 3.61 or 3.6, and this value here is 10.83, which should be periodic also here. The moments already have them. This value, this is 10.83, this is 10.83, this is 3.6, this is 3.6. Those are the values. Long, yes. Imagine doing that by using flexibility coefficient, for example. You're never gonna end it, never gonna finish. Really, really, really long. Now, how accurate this is it? How accurate this method is? Well, yesterday I run it. I used a SAP 2000 for this problem, and I'm gonna tell you what differences I got. If I find it somewhere over the rainbow. I think it's this one. Yes, I'm gonna show you how my office, how mess is my office. Yes, this is the problem that I ran yesterday using SAP 2000. This part here, and this is the moment diagram. Only lateral loads. I eliminated all the self weight and vertical loads, and I just doing this under that. So if we somehow have to prepare a table, let me see, and compare. Let's compare, for example, the moments. You know, exterior columns and exterior girders always are gonna present, or regularly, usually, they present more error than interior ones. So let's start with this one. For example, this column here at the base, which it should be one of the biggest errors because it's an exterior column at the base. But let's see what happened. The actual value, the correct value, or software if you want to, software value is for that column is 49.52. This is exterior column 49.52, and the method, the portal method that we got is 30. So if you do that, smart, 30. So if we want to calculate the error here, the error should be something like 19.52 divided by 30. 1952, that's a huge error. No, divided by 49. What I'm doing? 19.52 divided by 49.52. Well, it's still big. It's 39% error in that one, which is a lot. Now, if you talk about an interior column, for example, interior column, the software, let's talk about this one here. This is 53.79 and our value is 60. So you can see the error already there is nothing. I mean, it's 60 minus 60 minus 53.79 divided by 60. Again, smart. 53.79. That's 11.5% of error. That's really small error. Now let's talk about girders. I don't know. Let's compare, and this is moment, of course. Oh, let's continue with columns and then say in shear columns, exterior. If I use the shear in the columns in the exterior, for example, in this one, the same one, what is the shear diagram here? 13.98 was the shear for that column. 13.98, and in our problem we say that value was 10 here. I have a missed call. I don't know who is calling, but wait a second. I'm recording a lecture and I don't have editing button. So 13.98 minus 10, that will be something like 13.98, 3.98 divided by 13.98, 28.5%. In the shear for internal columns is shear for internal columns. This one, for example, we have 20 and this level 20, and the software has 16.24, meaning our error is gonna be like half of the other one, maybe 3.76 divided by 16.24, 23, yeah, it's 23.15, no half, but yeah, 23%. Now, what about the axial? The axial force, axial force, 9.52. I don't know, I'm tired. Axial, external, and I'm just comparing one for, I never did this before, so I'm doing it now live. 9.52 because I'm interested also. 9.52, and this is 9.52. That's the value for the axial forces, and we got 10.83. So the difference will be 10.83 minus 9.52 divided by 9.52. That's 13.7%. And if we calculate the axial for internal, axial for internal is 4.14 in our case, the correct one, 4.14, and in this other one is 3.61, the value that we got, and it will be 4.14 minus 3.61 divided by 4.14. 4.14 equals 12.8%. Okay. Are there errors? Yes, there are some errors. Can I still live with this type of errors? Yes, I can. I mean, if I know the magnitude of the errors, I know how to readjust it, or at least for a quick check if I need to. I don't have the software. I know that right now everything is about software, and if you run this in SAP 2000 or in Visual Analysis, you are gonna spend maybe 5 minutes, and then you're gonna ask me, why do I have to do this by hand if I have a software? Well, my answer will be because I did it and I want you to suffer like I did. But no, this is not the answer. The answer is because you need to know. You need to know how things were done before. You need to take, a feeling and appreciate what you have now. And you need to know also the type of assumptions that you can do for quick checkups. If you compare this with the literature, the literature says that the method of the portal for exterior columns average, because I only calculated one example, one column, etc., it goes between 24 and 30% approximately. Well, I have more. I have 39 in this part, or in this example we have more. Interior columns should go between 13 and 18%, and we went below that. Shear in exterior columns and is about the same range that we have, and the actuals always at the same time. One of the things that I didn't check that I want to check really quick now is in girders, for example. So if we check the moment diagram for the girders, this point in this girder, the value that we have is 26, for example, here, and the value that we had here, it was 36. So yeah, the error is also going to be there, and it's going to be kind of considerable there. And in this case we have 29, and in this case we have 36 in that girder. 29 here, 36 here. So 29, 36 minus 29, once again 36 minus 29 divided by 29, that will be 24%, and the literature says that it goes between 14 and 30% of error also. So we weren't that far away from the reality. Well, this is the method of the portal, and this is a big frame. If you have to do that once again by hand, and you have to use method of flexibilities and flexibility coefficient and redundance and superposition, it's gonna take you forever to do that. Right now I was explaining it, and it took me 1 hour to do that, step by step. And we are not done yet, because after that we need to do the shear and moment diagram. But lucky for us, shear and moment diagrams in this case are going to be straight lines basically all the time. So it's not going to be that difficult. And the zeros are going to be in the moment diagram at the hinge. Well, anyway, this is the method of the portal. I was planning on doing today also, I'm making you go through the cantilever method, but it took me a while, and I think that this is sufficient for today. But I really need you guys, and I'm talking to my students, of course, I really need you guys to go and check this method, review this method, try to solve this problem, and because you're gonna have one method like this in the exam, of course a smaller frame, but most definitely you're gonna have to do something like that. So next video I'm gonna do it about the cantilever method and the vertical loads, and then I'm gonna do one combining all the loads, applying superposition. See you next time, guys. I hope that you enjoy the video.